Now, in this ion sources, if you see what are the, when you design, what are the things you will look for? One is that what kind of species can make negative ions and what kind of intensity it can give. Not all the species or not all the elements make negative ions. So, what kind of negative ions can be made by that ion source, that will. And the beam quality. Beam quality, when we talk about, we talk of brightness as well as emittance. And emittance is the most important parameter. And in a layman language, you can say the emittance is nothing but similar to divergence. So if the divergence of beam is large, then of course that emittance is similar to that, but it is in the phase space. And therefore emittance should be, like divergence should be small, emittance also should be small. Now this is when we are talking of one-dimensional or two-dimensional trajectories. Then we talk of divergence. When we are talking of phase space, six-dimensional phase space, we talk of emittances. This I have discussed in one of the lectures in great detail. Then of course when ions are made out of any gas or material or element, what is the ionization efficiency, reliability, material utilization efficiency is equally important, because there are some cases where very small quantity in sometimes even less than milligrams of sample is available, and you have to use it for a pretty long time for and therefore the efficiency, material utilization efficiency of the ion source should be as much as possible. Then of course the from the point of view of operation, and it should be easy to do that. Duty cycle, whether a particular ion source we can run it for 100% time, duty cycle is 100%, or it has to be pulsed. So that also is one of the characteristics. And of course the source lifetime. So these are some of the characteristics which define whether the ion source is good or improvement is required. There are different kind of mechanisms which are responsible for example, for negative ions formation, which is very important. In fact, a lot of R&D is being done on these negative ion sources today. And you can see that one is radiative capture, where any element, neutral element X, picks up electron and make negative ion and emits a radiation, HNU. And it emits radiation or momentum transfer of third body. So this is one type of ion sources process which is involved in it. So this X prime, X negative, that means initially it is formed in excited state, and it will be emitting radiation here. Here you can see. Then polar dissociation. So you can see that there are different processes which are able to make these negative ions. And of course, the cross-section of each process will be different. Some of them will be very low. That means in that case, you can get intensity is very small. In other case, that may be very high, so you will be able to get. But normally, negative ion yield is very small. So you can see that it's a dissociative attachment or charge exchange. Now, as I mentioned, that alpha tross is based on this. So initially you make positive ions and then pass through a electronegative material or gas or vapors, and then it will pick up electrons. So that is so first is sputtering is done, and then the electrons are picked up. You can see here. Surface ionization is another one. Now you will see that Snick's ion source is very popular, not only for research point of view, but of course from the point of view of applications, because it can generate negative ions which are accelerated by protons and which are very useful for AMS sector. Now in this case you can see that there is an ionizer here, and the cesium is deposited here from what you do is that cesium is put here, which you heat it, and that cesium goes and gets deposited at various places. For example, at ionizer and cathode. So cesium is deposited at the surface, and when this is heated, then the cesium plus ions will be emitted out of it, and they will hit the sample here, which is a cathode, and then by sputtering, the negative ions will be. So sputtering basically is of the neutral atom or maybe positive, and those ones will pick up electrons from the cesium which is coming here, and this cesium is a good donor of electrons, because this outermost orbit of this cesium has only one electron, and the work function or the ionization energy of that electron is very small. So the electron can easily get attached with those either positive or the neutral ions which are coming out of this cathode. So for example, suppose I want to have let's say carbon negative ions. So I put a carbon sample here, hit with the cesium, and carbon will come out and it will pick up electrons from cesium vapors and cesium beams or the vapors, and then it can form negative ions, and which by proper voltage on the extractor you can extract. So this is a very, very important and very, very famous ion source which is used, is being manufactured, developed and manufactured by National Electrostatic Corporation in USA, which sells the Peloton accelerators, and the details can be found here. Now there is another source called alpha-TROS. This is equally important, and why I am showing is that, see, for example, in the case of Peloton or tandem accelerator, we need negative ions to be injected. Now you know that helium does not make negative ions in the ground state, and there are a lot of experiments have to be done with the alpha particle beam. So how to generate them? So this is a source which does that. What it does is it creates the helium plus beam which is coming from here, and then there is either cesium or rubidium vapors are put into here, either cesium or the rubidium here in the path of this He plus beam, and they pick up electrons from there, and then they are extracted. So it's a charge exchange. Positive helium picks up electrons and then becomes negative ions. So this is a boom to the low energy nuclear physics or nuclear physics people, or even atomic physics people who want to use He minus beam or He plus also in Peloton, because He plus means this He negative, that means helium negative beam will be first accelerated in the first part of the Peloton. Then in the stripper, it will be electrons will be stripped again, and it will be again a He plus, or it could be He plus plus, and it will be further accelerated. So both beams will be available, low energy beams of this and high energy beams of this. Of course, in the Peloton you can get only He plus, but these beams also will be available if it is, suppose you have a single stage kind of accelerator, then it will be possible to get this beam. So this is a very interesting So this is what is involved in it. So it's a charge exchange. And NEC again has developed this ion source for the experiments with the alpha beams. This is very popular for low energy experiments. And the process is again listed here, that He plus you can create from either dioplasmatron or any. There are several ion sources which can create positive ions. And then either you put in this will interact with either rubidium or cesium, and then the He minus beam or He, even the other, this process is again used for even proton beams, for making the negative ion beams, and even heavier beams. There is no problem. So this is one. There is another source which is very popular, and it is used not only at low energies but also at high energies accelerators, and that is dioplasmatron. See, most of the gases, ions, positive ions or even negative ions, they are made by making the plasma, and then you extract from this. Plasma is always neutral. That means it will contain not only positive ions, but electrons, but also some negative ions. So you can extract negative ions from that. Now, prior to dioplasmatron, which was called plasmatron, a single plasma was formed. In single plasmatron ion sources, intermediate electrode and magnets were not there, and hence the plasma density was low and low currents of the ions were extracted. In dioplasmatron sources, intermediate electrode and magnets is put. So what is done is that you feed the gas, and then there is a filament here which emits electrons, and electron interacts with the gas and makes it a plasma here. And plasma will have, let's say it is hydrogen gas, then plasma will have H plus, H minus, and electrons also. So, but what happens in the first plasma? The density of the plasma is low. So therefore the number of these particles, these ions, their density is low. So what you can do is that if you put intermediate electrode and then you have anode like this. So that is the structure of the dioplasma. So you have two plasmas here. In second plasma, the density of these ions is much higher, and therefore you can get higher currents from this second one instead of so this plasma was not there when in the case of plasmatron. Now this you can display. So what actually you are doing by doing this is you put one magnet also here. So what you are doing here is you are increasing the number of collisions to make it. So if the number of collisions are increased, then positive ions also will be increased density, and even some negative ion number also will increase. So you can see here that both in second plasma density of the plasma is high, and there is one more advantage by putting this magnet. One is that it is increasing the number of collisions, and secondly it is happening the magnetic field of, for example, if you take the motion of the ions will depend on the magnetic field. So for a particular magnetic field, you will find that since the positive ions are slightly lighter than the negative ions, so 2 electrons are added to this. So you will find the structure, if you see the structure of this plasma, it is like this, that at the center you have density of positive ions which is much higher, and at the periphery there will be a ring sort of thing where there will be negative ions. density also will be there. Of course, as I said that as compared to positive ions, the current of the probability of negative ions is only 1 to 2% only. So this current will be very small. This negative ion current will be very small. But this itself you can see. So what you can do is, when you are extracting here, if the axis of this was matched to the extractor here, then you will see that you are basically extracting the beam from here. So you will extract more of a positive ions. Now suppose you shift that axis of this extractor in such a way that this axis is facing the this ring, then you will find that more negative ions will be available, and therefore the negative ions in current will be enhanced by shifting by off-axis extraction of the beam. So this is what is basically is a dioplasmatron source. So you introduce one intermediate electrode and also a magnet. This I think I have discussed earlier also, but just to remind you and repeat it, because it's an important thing, is that helium is an inert gas and it has 2 electrons in the outermost orbits. So in fact, if you see various ions, positive, neutral and negative, in principle, if you go by the rules, then the configuration should be that here it is now, since the helium has 2 electrons, so one is removed here, so it is helium plus, so it should remain in 1s state. While neutral is 1s2, and 1s can have only 2, so it's a neutral. While if you want to make negative ions, then you have to add 1 extra neutron. So then the question is whether this 1 extra electron will sit in 2s or it will be somewhere else. This is a question. And if it sits in this, then negative, He negative will be formed in ground state. But it does not happen. It should be this, but it is not bound actually. The calculations as well as measurements show that it is not a bound state here. In fact, on the other hand, they found that this He negative is formed in this case at 1s, 2s, 2p, metastable state, and it's a metastable state which has a lifetime of about 360 microsecond with a binding energy of 77 milli electron volt. So that means if you want the alpha beam, you form helium negative ions which will have lifetime of about 359 microsecond, and you inject and accelerate it, because if your beam takes much longer time, more than this, then this electron will detach, and therefore before this time it should reach the high voltage terminal and it should get stripped out after acceleration. So that is what is. But this is a huge time. In the 360 microsecond, this beam can pass through the entire accelerator. So I would like to give the summary of this lecture. This is as follows. So in this lecture, we have discussed different types of ion sources, mainly SNCs, alpha-TROS, and dioplasmatron ion sources. Dioplasmatron ion sources can produce both positive and negative ions. Although helium is an inert gas, it forms negative ion in metastable state with lifetime of 359 microseconds and binding energy of 77 milli electron volts. Nitrogen 14 does not form negative ion and thus is responsible for high sensitivity for carbon 14 to carbon 12 ratio measurements for AMS studies. Thank you.